Hello, my name is Qiaomu from Southern University of Science and Technology. The work I will introduce is QEVIS, multi-grid visualization of a distributed query execution. The distributed query processing systems are designed to process and retrieve data from multiple servers and databases. These systems have become a cornerstone in modern applications and are now widely adopted by many leading companies. Many applications such as e-commerce, social media, and healthcare benefit greatly from the development of distributed query processing systems. However, as these systems grow in scale, understanding and diagnosing query execution becomes increasingly challenging for developers and analysts. We have collected the questions most commonly asked during the performance analysis and diagnosis, such as where does the time go, what is the bottleneck, and why is the query execution slower than expected. However, answering these questions is difficult due to the inherent complexity of distributed query executions. Factors include the vast number of atomic tasks running in parallel, unpredictable machine statuses, and complex concurrent programs. I will introduce the workflow of distributed query execution and take Hive as an example. When a query is submitted to the system, often in form of a circle statement like the one shown here, the query optimizer and the execution engine transform the input into a logical execution plan. As illustrated on this slide, the logical plan can be modeled as a directed cyclic graph. Here, the vertices represent jobs and the edges depict logical dependencies. Each of these jobs can be either a map job or a reducer job. For each job, it is composed of several operators. Let's use map 5 as a case. It sequentially executes 6 operators, including input, table scan, filter, select, reduce sync, and output. We further divided these operators into 3 phases. The first and the last operators are the input and output phases, respectively, while the remaining operators form the processing phase. Then, with a logical execution plan, the resource scheduler will generate tasks based on the jobs and their dependencies. The number of tasks generated for each job varies according to the workload and available resources. Finally, these tasks are assigned to different machines for execution. It's worth noting that the tasks from the same job can be executed on different machines. Based on the workflow described above, we have outlined the design tasks for our system, which involve visual analytics at 2 levels of granularity. Now, think of each job as a collection of operators functioning as components. Firstly, we provide an overview visualizing the execution of these jobs, offering a high-level perspective. Additionally, we have implemented a mechanism to measure job anomalies. These features enable analysts to pinpoint specific jobs that might require attention. For more in-depth insights, we focus on the visualization of tasks, the smallest units of execution. We've also established the capability to correlate the task executions with their respective machines. This correlation helps analysts in diagnosing abnormal execution patterns. Given a logical execution plan, we designed job view to present both timing information and the topology structure of jobs simultaneously. To achieve this, a straightforward method is the timeline-based approach, much like a Gantt chart, but enhanced with links to illustrate the dependencies. Such approach has been employed by existing tools like TestUI for job visualization. To enhance the user experience further, we have improved the layout using greedy-based method, which serves 3 key purposes. First, we aim to reduce visual clutter, often caused by overlapping edges. Second, we try to minimize the distance between parent nodes and their respective children, make it easier for users to follow the topology over time. And last, our layout design should reduce the space usage. Let's take a look at the algorithm's output, which we can find better than the existing visualization of the above aspects. Additionally, we have enriched the job view with 2 visual designs, which can be switched by users. The first is the parallelism mode. We employ a gradient color scheme from white to blue to represent the number of tasks executed concurrently. Notably, we use green to signify the time range when no tasks are running, which serves as an important cue for analysts. The second design is the phase mode, where we utilize 3 distinct colors to encode the percentage of time allocated to 3 key phases: input, processing, and output. To summarize, when examining the job view, users should focus on three specific scenarios: very long job execution, very low parallelism, and abnormal imbalanced time allocation for different phases. In practical scenarios, execution often involves hundreds of jobs and machines. It's crucial that our system provides a straightforward approach to pinpoint which jobs and machines are experiencing anomalies. To achieve this, we've devised a two-scoring method to quantify these anomalies. When we look at a specific job from the logical execution plan, we expect its tasks to exhibit similar workloads, resulting in similar time cost. Furthermore, these tasks should have no dependency relationships, indicating that they can be executed in parallel. To measure how much the actual task execution deviates from its ideal scenario, we've introduced two scoring metrics: APS abnormal parallelism score and ADS abnormal duration score. For APS, these two figures represent high parallelism and low parallelism respectively. We calculate APS by measuring the ratio of the blue region to the green region. As for ADS, our observations reveal that task execution times often form a normal distribution as depicted in this figure. However, when a few tasks experience long execution times, a long tail effect emerges in the distribution, as shown here. We quantify the anomaly by measuring the significance of this long tail effect. Specifically, we compare the cumulative distribution of these two scenarios and notice that the long-tailed case exhibits a larger shaded error. Thus, we quantify ADS by calculating the size of the shadowed region. Alright, with our scoring matrix, APS and ADS, we create a rows chart to offer a visual representation of the anomalies. In this chart, we use red and green sectors to denote APS and ADS values for tasks, while the remaining three colors represent ADS for different task phases. Furthermore, we have devised a performance matrix that features jobs as columns and machines as rows. This matrix provides a clear overview, enabling users to identify which job is experiencing abnormal execution on which machine. In order to get more in-depth insights, then we focus on visualizing the atomic tasks, which are the smallest units of execution. The most direct method for displaying these tasks is still the timeline-based approach. For example, in VIS employs the approach to visualize tasks as demonstrated in this figure. We've also adopted the same idea as shown in this figure. However, considering the large number of tasks generated and executed during query execution, it becomes challenging to observe individual tasks due to their very small size. Additionally, the large number of visual elements can result in visual clutter, hindering users' ability to discover group patterns. To address this, we have transformed the timeline-based approach into a scatter-based one. We use this animation to intuitively illustrate the process. Compared to the timeline-based approach, the scatter plot is more scalable for a large number of tasks and better preserves important patterns such as outliers. In our design for tasks, we employ the y-axis to represent the start times and the x-axis for the end times. Thus, all the tasks are placed on the top right side of the canvas since the end times are greater than the start times. The time cost of a task can be presented as a horizontal distance between the task and the diagonal line. When a user selects a specific task, an auxiliary line appears, running through the selected task and remaining parallel to the diagonal line. This feature aids users in easily comparing the time consumption of the selected task with others. Furthermore, for task dependencies, we've labeled the upstream tasks as providers and downstream as consumers. The x-axis denotes the start time of consumers, while the y-axis represents the end time of providers. Any abnormal dependencies are placed in the bottom left part of the canvas. Thus, the waiting time of consumers can be presented as the vertical distance between the dependency and the diagonal line. In practice, we've found distinct patterns that serve as indicators of query execution issues. In an ideal scenario, tasks exhibit a dense parallel pattern with all points closely aligned along the diagonal line. A dispersion pattern suggests multiple problems during execution, often resulting in a variant layout of tasks. A horizontal pattern indicates a situation where the system has enough workers but limited resources. In such cases, optimizing system parameters become essential. Vertical patterns typically appear when tasks are waiting for the completion of provider tasks. Outlier patterns indicate that specific tasks are suffering from issues like data skewness and deadlocks. The multiple cluster pattern indicates that the execution of a job is interrupted, usually caused by insufficient workers or suboptimal scheduling strategies. Understanding these patterns aids in diagnosing and improving query execution. In our system, we have incorporated a task view that displays all tasks, designed to offer a comprehensive overview of all atomic tasks. Furthermore, we have implemented an individualized task view for each machine, allowing users to correlate the tasks with the specific machine. We have also included additional auxiliary views to enhance exploration, which we will not discuss in detail. We encourage our audience to explore the full details in our paper or on our project website. Then we use a video to demonstrate the use of our system. In the query list, the users can easily check the status and basic information of a query. The first icon indicates whether a query is currently being executed or has been completed. By clicking the icon in this panel, user can download the query statement and view additional information. In this case, we have selected a query that takes longer time than expected. By clicking the last icon, the job view appears, providing a more detailed view of the job level execution. Two modes can be switched by clicking the mode icon. Users can also click on the performance metrics icon to see the chart that indicates anomalies in job execution on specific machines. From the job view, we can observe that the entire query has lasted more than 10 minutes, with a particularly long job M1. More importantly, a long gray region in the bar indicates that no tasks of job M1 are executed during this period. To explore the details further, we click on the last icon to display the entity list and the task view. When hovering the mouse on a job, the corresponding elements are highlighted. Note that the purple color is used to indicate the current selection, while red and blue colors indicate the upstream and downstream elements respectively. We observe that the tasks of M1 form two groups, which is the multi-cluster pattern. This pattern is always caused by insufficient resources or machine problems. Then we check the reasons with the entity list. By clicking the triangle icon of M1, we can observe the timing information of tasks executed on each machine. We observe that the tasks of job M1 in the right bottom corner are executed on machine DBG18, which executes very few tasks compared to other machines. It suggests that the resource scheduler allocates a small number of tasks to this machine, confirming that DBG18 is a problematic machine. Additionally, M24 is another long job, and there may be other issues in the cluster. By mousing over M24 and highlighting the tasks in the task view, we find two tasks significantly longer than the other tasks. Clicking a task in the task view automatically locates the elements in the entity list, and we find that these two long tasks are executed on machine DB19. Then we check the CPU and memory resources, and find that DBG19 has very high CPU utilization, which can also cause slow query execution. This is another execution after we remove these two machines from the cluster. By clicking this icon, we can align the selected job views from different executions and make a clear comparison. We find that the second execution is much quicker than the previous one. Additionally, the task view also shows a more obvious parallel pattern than the previous execution. QEVIS also supports simulating completed query executions, allowing users to replay how the query is executed. Users can adjust the speed of animation as needed. In summary, we have designed a layout algorithm for depicting execution overview, scoring method to identify execution anomalies, a scatter plot-based visualization for displaying numerous tasks, and a visual analytics system with multiple coordinated views. In the future, we will expand our tool to more distributed computing systems such as Spark and Flink. We are also suggested by the domain users to integrate additional automatic debugging approaches. They hope our tool can provide explanation for the existing debug methods. That's all about my presentation. Thanks for your attention.